So thanks, everyone. This is the third series of talks, and this one is on SMAP. And I want to first acknowledge co-author, co-presenter on this, which is Sirajota Kalsa, live from the Czech Republic or Czechia. And so appreciate Sirajota. Sirajota is really the SMAP expert at NSIDC, I would say, more so than I am, for sure. So I'll give the first part of the talk, and then Sirajota's will carry on, and has, I think, focusing a lot on the validation, which will be interesting. So this will, I'll kind of do more of the background. So yeah, so I titled this SMAP out of it, which I always think of this when I think of SMAP. And so, yeah. So SMAP stands for Soil Moisture Active Passive. It was launched January 31st, 2015, so it had its 10th birthday not too long ago, going on 10 and a half, I guess now. Sun synchronous orbit, 6 a.m. descending pass, meaning 6 p.m. ascending pass, 8-day full repeat orbit, and it gets near global coverage every 3 days. So it's at least one part of it is, well, it's a microwave instrument, one part being passive microwave, so that's the emission, natural emission from the Earth. And just before we get into the details of SMAP itself, just kind of look at this as background. So, you know, the sun emits in the visible range at its peak, very high energy. The Earth emits in the infrared range, kind of the heat is at its peak, but it also emits in the microwave range. And that's what we look at when we have passive microwave. We're measuring the microwave energy being emitted by the Earth, but it's very low energy. You can see these peaks here. There really is no peak for the microwave because it's too small to really show up there. So to get a lot of
well, where would it be? Where would the peak be on it?
well, I didn't really. This
Oh,
kind
it's
of
way out there.
it's out here, yeah.
Yeah.
Yeah, this figure stops in the infrared, and I just kind of extended it out, so I'm not sure exactly. But it's basically, it would be really tiny little, probably not even visible bump there, yeah. So to collect enough energy to really work with as far as geophysical parameters, you need either a large antenna, or you gotta look at it for a long time to collect the energy, but you can't do that in a satellite. Or you gotta collect over a very wide area, which means low spatial resolution. Now, the large antenna is a challenge for satellite sensors because how big of a thing can you launch? If you remember from it or watched the passive microwave sea ice one, like the SSMI, SSMIS, you know, you had these smaller antennas that you could package on to the satellite, and that really limited your resolution. But SMAP actually has a big antenna, even though it's launched in space. You know, SSMIS is about a 0.5 meter. The Amateur 2, which is the newer passive microwave, is about 2 meters. But SMAP is actually 6 meters. So that's, you know, that's like bigger than this room or close to, yeah. So it's huge. And the way they do it is it's not a solid antenna. It's a mesh antenna that folds up, kind of like an umbrella. So they can pack it together. It's not too heavy. It doesn't take up much room, so they can put it in the rocket to launch it, and then it pops open. And then that's a picture of it in one of the clean rooms. And if you look, you can see it's mesh because you can see the people through the antenna. So the antenna is kind of above the ground with the support beneath it, and that allows you to get reasonable resolution even at low frequencies. Like 1 gigahertz. So resolution, I also mentioned that is dependent on the frequency. So higher frequency, you get higher resolution, finer detail. But when you go down to lower frequencies, you get less detail. And 1.4 gigahertz is quite low frequency for microwave, and that would mean big footprints. But with this big antenna, you can get roughly 36 by 47 kilometer footprints, which is still low resolution, but it's reasonable to be able to detect things like soil moisture. So SMAP had these 5 science objectives. Obviously, it's mostly detecting soil moisture. But that goes into a lot of important processes that are relevant for understanding the Earth, the terrestrial water, energy, carbon cycles, energy and water fluxes, the net carbon flux, especially in forested areas. And then, the idea will help forecast scale weather forecasting. And then soil moisture is an indication of, obviously rain and potentially extreme weather, and so it can help with flood prediction and particularly drought monitoring. So the instrument, it's got two instruments on it. One is the passive microwave that I talked about, 1.4 gigahertz. It's got different polarizations, horizontal and vertical, and it's got what's called these Stokes parameters, which are different polarizations, two other polarizations that help radio frequency interference. Do folks know what radio frequency interference is? Kind of, yeah. It's basically like cell phones and things like that. So, if you're detecting emitted energy, if a cell phone or a satellite dish or something is emitting energy, that will also get picked up by the satellite. And unfortunately, due to our modern society and modern conveniences, these frequencies are bleeding into some of the geophysical channels that we use. And so you'll get these weird basically false, as far as geophysics, false hits. And so there's ways to kind of filter that out and or attenuate that. And that's what those Stokes parameters help to do. And then there's a radar, a synthetic aperture radar, SAR. And so that's an active instrument that's sending down the pulse and getting the reflection and backscatter. Also at roughly 1.4 gigahertz at L band, which I'll do a quick discursion with this. You may have heard of L band and other C band and things like that. And they're basically these are just different ways of describing the electromagnetic energy, generally in the microwave range. I actually found this kind of interesting, where these come from. Like L stand for long, that kind of makes sense. And then S is short because it's shorter wavelengths. There's the C, which is compromise. I think I'm not sure where that came from. X, which is crosshair, makes sense. And then the Germans got into it with Kurz, meaning short. That's the K bands. And there's like a KU, which is under, so it's a lower frequency, and then above higher frequency. Then you get to the very high B, standing for very high frequency. And then when it goes higher than that, they just did W, which is the letter after B. So yeah, the logic of these is kind of, I don't know, interesting, but they were developed actually during World War II. And they came up with these names, and that was when radar was really coming into its own and being used a lot for defense purposes. And they developed these, and these have kind of been used since then. There are some different conventions. This is like the IEEE standard, I think most commonly used. In terms of like geophysics and monitoring Earth, the L and the C are at least for radars, are kind of the common ones. Although the K bands are used as well as sometimes the X. So, but not really the V or the W much. So
and Walt, I think like FM radio is up to about 100 megahertz, right?
Yeah, that's
something right
megahertz.
around there. So
Yeah.
Obviously a lot longer.
Right.
Order of magnitude.
Yeah.
Okay, we could pause there just for a second. I'll just mention that if you're looking at sea ice with SAR, most favored one is C, I guess compromise, because you get a good distinction of ice types that way. But sometimes they use L because it penetrates more, so you can see between like flows and ridges and deeper into the ice that way.
Yeah. So these different bands, interact with the surface in different ways, and so depending on what you want to look at, it depends on what bands or frequencies or wavelengths you want to do. So in terms of how the microwaves work, you get the brightness temperature, which is kind of what's observed or is what's observed by a passive microwave sensor, which is most simplified, it's a function of the emissivity and the physical temperature. So it's pretty straightforward, but the emissivity is a pretty complex function of a lot of different things. It's a function of the frequency and the polarization, and the incidence angle, and then the characteristics of what you're observing, the body that you're observing, particularly the dielectric constant, which basically it determines how well electromagnetic energy flows through the sort of body or is emitted by it. And so that's kind of one of the key things. And then in active, you're sending down a signal and then you're getting the reflection, or oftentimes for radar, it's called backscatter. And that's this sigma naught is what that's called. Sorry, I should put that up, but that's the sigma 0. That's what's measured by the satellite. And so it's basically a measure of the magnitude of how much of that incident signal gets reflected back to the sensor. And that's dependent on like the surface roughness and then the frequency, the polarization, and well, the roughness is a part of one of the body's characteristics as well, including the dielectric constant. So you've got these two different ways of doing that. And you know, just a real simplified way of looking at this, it's just liquid water has a high dielectric constant, very high, like 80. Whereas dry soil is much lower, less than 5. And so there's a big contrast between those. And the dielectric constant means higher higher dielectric constant, higher reflectivity, and lower emissivity. So soil moisture, if you have higher soil moisture, the brightness temperature tends to be lower and the backscatter tends to be higher. And so that's basically, I mean, there's obviously a lot of things that go into this, but that's the basics of it. And the advantage of combining the active and the passive microwave, like you said, you know, the dielectric constant is really big difference. So it's really sensitive. The passive microwave is really sensitive to soil moisture. So it's really good at detecting how much moisture is in the soil, but it's still relatively low spatial resolution. Typically the standard resolution is 36 kilometers gridded. The SAR is higher resolution, much higher resolution, like around 3 kilometers when it's gridded. But it has a lower sensitivity to the soil moisture. It's really affected a lot by the surface roughness in the vegetation. So you don't, if you just use the SAR, you would have trouble kind of distinguishing the soil moisture. But you get the resolution from the SAR, and you get the soil moisture sensitivity from the passive microwave. So you combine those in like kind of a medium resolution, and you get decent resolution with decent sensitivity. So
one question.
yes,
On the dielectric, in sort of the electrical world, a dielectric is an insulator.
yeah.
But here we're saying that high dielectric is a reflector.
Well, it's an
Is that
indication of
same
how
the same thing we're talking about?
I think they're not quite the same thing. I think they're used differently. This is like the dielectric constant. Yeah. So I think it means different things.
Yeah, okay,
Yeah. Yeah.
Sarah here. The confusion could be avoided by using the word permittivity. That's another word for
Yeah,
yeah.
Yeah, permittivity is more common, maybe more commonly used, but yeah. Thanks, Sergio. So as an example, this is from 2015. And this is like the 36 kilometer passive. So you can see these are the in swaths, so that gives you kind of a daily coverage on that day. And you can see it's pretty blocky, but you see some good contrast there. And then you do the radar, and it's a lot more detailed, but less coverage. And then if you combine them, you kind of get this in between. And so you use it. So that was the design of this. That's why it's soil moisture active passive. You got active and passive together. And I'm showing here 2015. You're probably like, why are you showing 2015? I mean, geez, that's like, so why don't you show something newer? Well, alas. Unfortunately, the radar stopped working on July 7th, 2015. So not long after launch, 6 months or so after launch. So it became kind of SMAP as opposed to SMAP. So that was unfortunate that failed so quickly. But they did go to plan B, which is Sentinel-1. It's an ESA sensor, and it's radar as well. And so you can use the radar from that. Now Sentinel-1 is C-band instead of L-band, so it's not the same frequency, same band, but it's closest in orbit, and that's of course important because you want to have simultaneous measurements. That was one of the great things about SMAP is you had a radar and a passive microwave on the same instrument, so you're collecting data from exactly the same place at exactly the same time. Can't do it with a different satellite, but you can at least come close. And so the C-band, even though it's C-band, the lag was less and you could get more coincidence information. So you could still get some radar retrievals. So again, active. Now, the limitation with Sentinel-1 is that unlike the SMAP active SAR radar, it's not, it doesn't have the same coverage. It's not on all the time. So the coverage is much sparser, so it's still definitely a degradation in terms of the coverage from the radar. But at least it's something that you can get some of the higher resolution data from it. So yeah, this is from, well, that's from August, so yeah. When you're driving soil moisture, the biggest problem is vegetation. You want the emission from the soil and how wet it is, and you've got these stupid trees and plants and all stuff in front. Yeah, this is like, no one likes deforestation, but if you're a SMAP scientist, you're probably like, all right, Brazil, cut down all the forests. It'll be much easier. No. And so, yeah, the vegetation attenuates the energy, the energy coming from the soil, it hits the vegetation, gets absorbed and scattered, and so you lose it. But then it also emits its own energy too. So what you're seeing from the satellite is the soil and the vegetation above it. And so it's really important to have some understanding what type of vegetation it is and what the water content is. You also have to worry a little bit about the temperature because it's dependent on the temperature as well. So you want to know what the physical temperature is so you can get the emissivity and the dielectric constant dielectric properties for that. So,
but the emissivity dominates, right? At these wavelengths.
Yeah, I think in general, I know for sea ice, it definitely does, but that's because it's very cold. You have a lot more temperature variability over like soil moisture areas. So I think it's more important, but still the emissivity, yeah, it does dominate.
And you have to worry about different temperatures, right? It's not just the top of atmosphere temperature.
Yeah, well, it's because you're getting the signal basically at the top of the atmosphere, so it's the temperatures throughout the atmosphere.
Right.
Yeah. Now at L band, well, I think I get into this,
Okay.
if I remember. Yeah, L band, you're penetrating through the atmosphere. There's not much emission by the atmosphere or attenuation.
Yeah.
So that's actually one reason to use the 1.4 gigahertz as opposed to these other channels, like the higher frequency channels that you have. Yes.
So then it's just surface temperature. You don't have to say this is the trees and this is temperature of the trees and this is the temperature of the rocks.
Yeah, ideally you would do that, but yeah, in practice, what they do corrections. I'll talk a little bit about some of that, based on ancillary data to get the, kind of separate out the effects of those and really, get what the temperature is at the surface or even a little bit below the surface because it penetrates into the surface some. So it's kind of like I think it's like the upper 5 centimeters or so, depending on the soil type and so forth. But yeah, you can like things like AMSR or SSMIS, you can do soil moisture, and actually AMSR does have soil moisture products, but they only go down to 6.9 gigahertz. And those are not as optimal for soil moisture. And so the L band is much better. This is an example on the right, just showing the attenuation. So the biomass is along the x-axis, which basically means more vegetation moving towards the right. And so you can see there's some attenuation, but it's much less at the 1.4 gigahertz. And it's pretty linear too, compared to the other channels. There's about 5 centimeters. Maybe for some people who are early risers, 6 a.m. is a good time of day. Not as much for me, although I'm not too bad anymore. But anyways, for a lot of people, 6 a.m. is not the best time of day, but for SMAP it is, because it's the early morning, that kind of everything, the temperatures kind of attenuate. So again, kind of looking at the temperatures, the air temperature near the surface, the vegetation temperature, the soil, you're not getting this kind of, the sun's high and really heating things up. And so you get this kind of, this is actually like you're talking about corn, it's like the effective temperature is kind of the total temperature that it's seeing. But it's, based on these, and it's easier to, basically that becomes close to the the actual soil temperature. And that shows on the right there how the temperature varies through the time of day. And there's kind of the crossovers, which is about 6 a.m. and 6 p.m. So that's why that orbit was specifically chosen to kind of avoid the peak day or middle of the night. And you get less atmospheric effect. So everything's more uniform. And so 6 a.m. And then you also, again, you get the 6 p.m. as well. And there is data for that as well collected, but the 6 a.m. is better because you haven't had the heating through the day. So yeah, looking at these, you need to know a lot of things to try to pull out the actual soil moisture from the overall signal. And that's going to vary by surface type. Water, if you've got lakes or rivers in your signal, that affects things because of course it's sensitive to the water. And the angle, which is affected by the surface elevation and the slope. And then the type of soil is also important. Oh, Sir Joe, he gets up at 5:30. Okay. So that's good for him. Yeah, so all of these things are relatively stable. They don't change very much. So these can be put into static ancillary fields, and that's basically what's done. I mean, obviously things do change some, but at large scales, these can be kind of assumed to be constant. So those just are static files and reads them in and then uses those in the corrections. And then there's these dynamic fields, the land cover class. There's like a cropland database, the Modus land classification. That's not like updated daily. I think it's updated quarterly, yearly, something like that. But it is technically dynamic. And then, yeah, there's these lookup tables, and then the precipitation, which is from reanalyses. Yeah.
Are those used just for the level 4 data or also the level 3?
These are the level 3 too. Yeah. Yeah, these, because you still need to know that for like to pull out the soil moisture. Some of these might just be in the level 4, but I think most of these are in the level 3 too. Yeah.
My suspicion is that level 4 actually has even more ancillary files.
Yeah, level 4. Yeah, which I'll talk about. That's using models, and so there's things in the model that are additional and may pull in other data as well. Yeah. So yeah, these are. You get your vegetation parameters, so you know what the vegetation is. And then, the GMAO reanalysis, so that's atmospheric reanalyses that are run, and they can calculate the soil temperature, air temperature based on those reanalyses to help pull that out. Yeah.
I mentioned the snow IMS. We archived that for National Weather Service, National Snow and Ice, or National Ice Center.
Yeah.
But I'm guessing that the NASA algorithm pulls it from the NOAA PDA. It's
Probably, yeah, that would be my guess. Yeah. So just an example field. This is I think this is the 9th one. I forgot to put that in. But yeah, this is just a recent. There are quick look products and new real time products, and so we can look pretty recently. And you may remember last week, was it Wednesday? I think we had like the big downpour storms come through. So that was, I think, the 14th. So you can see the difference here in the Northwest Colorado, where it's dry, and then on the 16th it's much wetter. So it really does a good job of picking up, very events, synoptic events, and so forth, and tracking those. So one more thing, I didn't really talk about it before, although it was kind of mentioned, I think, but frozen soil also has a low dielectric constant, and very much like dry soil. You've got water, but it's frozen. And so you could do something with that. You could do a freeze thaw algorithm. So that's another standard product that is used. There's lots of equations there, but it's basically a polarization ratio, which is similar to like what's done for snow cover or sea ice in particular. And it just calculates, and then there's a threshold for thawed versus frozen. And then it does some post processing. If it's above freezing, then it's probably not frozen. And then also brings in some other ancillary data. So it's just basically a binary field. It gives you the soil moisture and the freeze thaw. So it's, you have you have like the soil moisture product actually has a freeze thaw or a frozen ground flag in it to tell you that there's no soil moisture there, and then vice versa, you have the actual freeze thaw product, so, yes. Yeah, and here's an example. So you get the morning and the evening overpasses. And so they do kind of this binary check, you know, they're both showing frozen, then you are confident that it's frozen. They're both showing thawed, you can be confident it's thawed, but when it's, you know, frozen in the morning and thawed in the afternoon, you're in a transitional state. So it's basically, you have this diurnal, it's freezing at night and it's thawing during the day, transitional. And if you have, this one's a little bit of a weird one and I think quite rare, where it's thawed in the morning and then frozen in the evening. So that would be, you know, some sort of cold front maybe coming in or something. And it's called, yeah, inverse transitional. So this is just an example, February 15th, you know, a lot of frozen ground up north, in the midst of winter. And then recently May, you know, there's still some frozen ground up in the high north, but most of, the thing, you know, the surface layer has thawed. Yeah.
Is all of this in conjunction with Sentinel-1?
No,
Or-
so there, yeah, I should make that clear. I mean, there are products, I think I have a list of the products.
Like, because some are passive. You can-
Yeah. So there are products that are just the passive, and then there are products that are the combined passive and radar, yeah.
How deep into the ground would like the frozen and thawed?
This is mostly surface, I mean, maybe the first few centimeters, so it's not detecting permafrost or anything like that, it's detecting the upper layer, the active layer, yeah, yeah. Then there's these level 4 products, and these are kind of value-added products. So level 4 is generally when you're doing additional processing, bringing in additional things and or modeling, and this is specifically modeling. So you can take the data from SMAP, but then put it into a model that then can simulate other things. So for example, root zone soil moisture, you know, we only get, like I said, about maybe the upper 5 centimeters or so from the satellite. But if you have a model, a land model with, you know, the soil depth, you can take that and then use the model to calculate soil moisture down to 100 centimeters, which gets you more into the root zone, which is of course important for a lot of vegetation to know, not just how much moisture is at the surface, but down where the roots are. And then you get this ecosystem exchange, which is basically a carbon flux or carbon balance. And then this primary production, which is basically vegetation. So this is an example back from 2024, February, winter in the US, you know, except in the south where you have some vegetation. And the green, the blue is more vegetation, and you get to May, it's springtime, and everything's getting green, as you would expect. So yeah, here's the products. And I won't read through all these, but you can see there's this radiometer, soil moisture, radiometer plus radar, soil moisture, radiometer, freeze thaw, soil moisture, freeze thaw. And then there's the different levels, level 2, level 3, and then these level 4. This is not complete. These are kind of the main products. And then I'll mention there are these Lance near real time products for some of these, the soil moisture, I think primarily. We also have this RSUR enhanced SMAP products. That's that follows on the other passive microwave products. So, and you see
I got to insert here because the SMAP science team makes a big deal about this. That's not a standard SMAP product.
The RSUR, correct, yes, yes. Yeah, that's basically coming out of the measures project, yes. Yeah, there are other, yeah.
NSIDC has a role in that. Mary Jo was part of that.
Yeah, Mary Jo developed that, Mary Jo and Molly Hardman now, yeah. So I maybe should have put that separate from the main table, but that's a good point. So let's see, don't want to go, yeah, almost done here. So there are some cousins of SMAP. There are other 1.4 gigahertz sensors, or have been. One is SMOS, which is soil moisture, ocean salinity. And then there's Aquarius. Aquarius is NASA, launched in 2011. That only lasted about 4 years. And so don't have a long data record, but we do have those data products at NSIDC. It's a little bit different. Each of these have a little bit different configurations in terms of how they do their satellite antenna, how they do the antennas. They have different sensitivities and different values for different things. And one of the things like the Aquarius was very focused on surface, on sea surface salinity. The 1.4 gigahertz is are also sensitive to the salinity of the water. And so that's another use for it. The SMOS, you can see, is kind of a dual, looking at trying to get soil moisture and ocean salinity. Aquarius was kind of focused on the ocean salinity, so it was kind of the center when everything was kind of tuned to optimize that. SMAP was more optimized for soil moisture on land. But they're all 1.4 gigahertz. And they're all, you know, kind of collecting that same kind of signal in terms of the radiometer. And so some of these products, there are surface salinity products from SMAP, actually. These are not, well, I think these are, sure, Jody, you can tell me if these are actual science team products. I think they are, at least some of them are. But they're hosted at PODAC because they're more ocean products. So we don't have all of the SMAP products here. But basically emissivity varies with salinity, so you can quite nicely get that. Then another thing I talked about, you know, it's sensitive to the freeze and the thaw. So that means it can be used for sea ice in the ocean. And the L-band is particularly useful for thin ice because it penetrates down through the ice and actually can tell you ice thickness. You know, normally the channels that we use for passive microwave are getting really close to the surface. So you can't really tell much about the thickness from the 19 gigahertz or 37 gigahertz. You could just tell whether whether there's ice there or not. But L-band actually penetrates through, so you get some emission from the ocean below that penetrates through up to a certain thickness of the ice. I would generally say 50 centimeters. The SMOS folks always claim they get to a meter thickness. They can estimate. I'm skeptical of that, but at least 50 centimeters. But what's nice with that is things like ISAT2 and Cryosat2 altimeters, where you're measuring the elevation. You know, if it's thin, it's really, your errors are really high because you can only measure the elevation to a certain precision. And if it's thin, you've got a large uncertainty there. But SMOS is really good for thin ice. And so you can combine those together. So the Europeans have done that. They have merged Cryosat2 SMOS sea ice thickness. You use the SMOS for the thin ice, and then the ice, it transitions to Cryosat2 for the thick ice. Sir Joda, I think you are now up, and not completely different, but I had to put SMAP crackle on top here. So all right, I will stop sharing, and Sir Joda, if you are ready to share. Transition.
Question is you're transitioning.
Yeah.
Right? In terms of the passive microwave part from SMAP,
Mhm.
what kind of emissivity are we talking about? I mean, this is far from a black body, right?
Yeah.
So
yeah.
what kind of, 0 to 1, but what kind of emissivity are we talking about?
You know, I don't know right off the top of my head, exactly what I know for like, ocean, I know for sea ice, it's better, like water is like point something, I think. And the ice is more like 0.7, 0.8, yeah. But I don't know for like soil exactly what it is.
In the microwave.
Yeah, the microwave, yeah, so. Yeah, all right, so Joda. You can see your slides, you put it in the presentation mode. I think you want to swap your screen, swap your monitor? We're seeing your notes in like the next slide preview kind of thing. Yeah, presenter view, yeah. And we're not hearing you right now if you're saying anything. Oh yeah, you are, it looks like you're muted. So when you're ready to come off mute.
All right, I had to unmute, I had to stop sharing and unmute so we can troubleshoot this because I was in presentation mode. And okay, let's try that. How about that?
Oh, let's see, there it goes. That's right, that looks good. Yep.
Okay, but it put the participant panel. Okay, all right, I think we're good to go then. Hey, Thanks for the opportunity to give you a little bit more about SMAP well, I'm going to start with history and then current efforts to improve the algorithms in force. Oh, come on. Next. All right, good. So I'm going to start with talking about product design. Okay, so yeah, SMAP, product design and algorithm development. And I used some slides from Andreas Gollander, who heads validation for SMAP, and he made presentation at the SMAP science team meeting, made some really good slides, and so I'll be using those after I first talk about metadata. Okay, so the SMAP product design began like 15 years ago, 5 years before launch. Right about that time, the NASA's metadata evolution for NASA data systems, the MENS project, issued its report recommending adoption of the international metadata standard ISO 19115. Barry Weiss, who was the SMAP product architect, really took this to heart and decided to create complete ISO metadata and embed that in the HDF files, as well as deliver it as a separate a sidecar file in ISO 19139 in a markup. Okay, and that actually was model was actually adapted by ISAT2 as well. So you can see there was this feature article that was published in 2020 about applying international metadata standards to NASA Earth Science. And in that, it was essentially an interview with Barry Weiss. And in that, he is quoted as saying, as we generate more data, the need for metadata grows enormously. People not only need to find out what they're look for. In other words, they need metadata to find what they're looking for, but they also need to be able to assess the quality and content to determine whether it's really what they want, whether it suits their purposes. So metadata are integral components of NASA Earth Science data, ensuring their content and quality are crucial. So that's why he jumped on the bandwagon, and he and I were working together because I actually led the MENS study, which was a Tiger team spun up by Andy Mitchell. And then he gave a webinar that I linked to there. It was pretty cool. He really walks through the metadata standard, and then in the webinar, he asked these questions. And one of them was, what concerns do you have with regard to the adoption of a specific metadata standard? You got to realize, the history is it was sort of a Wild West, and people kind of threw in whatever metadata they thought was appropriate in whatever format they wanted, right? And so this was really an attempt to standardize all this using an international standard. Now, I know there was a DIF has been around for a long time. The GCMD DIF, directory interchange format, but that's directory level metadata. This would be, granule by granule, right? Some of it's granule by granule, but still DIF did not cover all the things. If I showed you the metadata, you could see all the different facets in terms of lineage and what have you. But these were the responses. Standards 1, you hear this a lot, should be lightweight. Don't burden us telling us to fill out a lot of different metadata attributes. It should be specific to geospatial data. It should be compatible with existing community tools. The current metadata model is a moving target. That applied to, ECS had its release B, metadata model, which was largely based on 19115. But GCMD and ECS had not really signed on to that, and frankly, still haven't. Somebody's saying, well, I'm still working my way up the metadata learning curve, indicating there are issues in learning. And I love this one, having questions about the standard and not knowing where to go for answers. there's inconsistency how the standard is implemented, because there are often multiple ways to specify a particular attribute. Now, that last point points to the need of having a profile. And that was one of the recommendations of MENS, was that NASA have an ISO 19115, a NASA-specific profile of 19115. All right, again, wasn't implemented. Now I'm going to talk about SMAP-VEX. So SMAP-VEX is the SMAP validation experiments, plural. They spend quite a bit of time. In fact, I looked it up. NSIDC currently has published 41 SMAP-VEX datasets. And so this is all the stuff that's collected on the ground to try to validate, and in the case I'm going to talk about, improve SMAP data. So I'm going to specifically talk about SMAP-VEX 19 to 22. So there was the first one was to improve soil moisture and vegetation opacity. In other words, vegetation water content in forests. And these two SMAP maps, April and July 22, those two, you probably can't see my pointer. Can you see my mouse? Hello, am I still there? Do I have an audience?
Can you hear us?
Yeah.
Yeah. We
Can you see my cursor?
Yes.
Yes.
Okay, good. So this is Millbrook and
Massachusetts.
Massachusetts. I was gonna say Massachusetts, but I thought there was a place in Massachusetts. Thank you, but that was Lauren.
Yeah.
Yeah, we're currently working on this data that came from this experiment. Okay, so that's forest. That's what that was about. And then they did then followed on with the boreal forest measurements. Okay, so I'm going to describe these measurements because they're these field campaigns, because they're really cool. I mean, I like what they're doing. But why forests? Okay, forests cover 30% of the land surface. They are responsible for a third of the total global photosynthetic activity, and they store about a third of the total carbon and account for and are habitat for countless species. And then, of course, forests represent a critical resource for human activities, timber, food, and fuel. This map here shows the areas that are flagged because of dense vegetation, and that's VOD greater than, I forgot the number, some cutoff where they don't believe that the algorithm can perform well. Okay, so that's flagged in the quality metadata of each granule. And so look at the US. You see maps of SMAP soil moisture over the North America, continuous all the time. If you were actually applying the quality flags, you'd only see data in the gray areas. And a lot of people don't. And you see lots of publications where they're using that data along the eastern seaboard all the time, but it is not flagged as optimal. All right. So as Walt described, you need the vegetation optical depth, which is really to the water content, in order to disentangle that contribution to the received radiation. And I'm talking passive here. This is all about passive. The radiometer measurements. Okay, you need the vegetation optical depth. And there are two parameters that determine that. That's the scattering, the single scattering, and then the temperature. But it's not just the trees; it is also the undergrowth. Okay, because that obviously is between the surface and the atmosphere, or between the surface and the receiver. Okay, then also, as Walt mentioned, to resolve the soil moisture, you need the soil permittivity. And that's a function of what's called surface roughness. It's not quite the same thing as like Z0, irregularity. It's like it's texture and content, and then the soil temperature. So you need both the vegetation temperature and the soil temperature, and it's what we're saying. It's good to have these the same. And that's why that could, at the 6 a.m., 6 p.m. All right, so the soil permittivity is going to be a function of the soil composition. So the leaf litter, moss, lichen, all that influence that. And then the other parameter that's used is the characterization of the air soil interface, the H parameter. If you look at the equations, you see where that comes in. But I'm going to talk about the experiment because that's what's cool. So they needed to, first of all, deploy sensors, bury sensors in the ground, the dielectric, to actually directly measure the dielectric constant, buried sensors as well as probes that they went around sticking to the ground. And then, as I said, you need to know the soil texture. That means the clay, sand, and organic matter. Well, clay, sand. What's the third part of soil texture? It's not soil organic content. God, I'm sorry. Maybe it's like the rocks. Anyway. And then, as I said, the litter and moss layer, and obviously their water content can vary, and their characteristics determine their permittivity. All right, so this is the plot layout in the left. This is their sampling strategy, and this kind of map is actually one of the parts of the SMAP data that we've published. So the circles are manual soil moisture measurements, and then you've got a leaf area index. So you look up at the vegetation above you to get that parameter. There are tools for doing that. Oops, sorry. Bulk density measurement location are the triangles, and then the station, the red triangle, is measuring air temperature, and then upward looking camera, and then it's hooked up to these to the soil moisture probes that are buried in the earth. So that's the far right is an example of one of those stations. I wasn't there, so I don't know exactly what it looked like, but this is Andreas. It was very thorough in documenting this. So as Walt said, the basic principle is that the more water, the more attenuation, right? The more water in the trees and vegetation. However, the vegetation structure, there's scattering of the signal, and its density, right? How far apart the trees are spaced, makes it really tricky to link the transmissivity of the ground emitted radiation and the vegetation parameters. So these are things that could be directly measured. The water content of the trees and leaves and everything else by cutting and grinding up and desiccating it and whatever. See how much usually what's done is how much does the weight change after chopping it up and desiccating it, and then the before and after measure is how much water you lost. And then you can insert dielectric sensors in the tree itself, and then you can get the structure. Yeah, here we go. All this was done in SMAPX. The structure of the vegetation, this is just trees, not the ground, with laser scanners from all sorts of platforms, and then the phenology from optical. That's the leaf area index. It can tell you the phenology. It's how many what the stage of the leaf on leaf off is. And then he mentions the GNSS transmissivity. And I'm going to show a slide on that just because it was pretty cool what they did. All right, so he went through in his presentation. I'm not going to show all of them, just some of them to show. So here are the sensors in the tree itself for measuring tree permittivity. Oh, I better get going. Okay, and this is the the cameras, the upward-looking cameras. I showed you one of those stations, and there's a time series showing a VOD, tree permittivity, and then the leaf area index from the upward-looking cameras. And then the laser scanning, somebody walking around with one, someone doing from aircraft, what have you. And then this is the LAI showing how it the LAI from is like the Motors product, right? How the scatter diagram, comparing that with what was derived from the zenith looking cameras, and then GNSS transmissivity. That's where you take GNSS signals and you have a station outside the canopy and a station inside receiver. And then it's L-band too, GNSS, that's GPS and other navigations, global navigation satellite systems. You measure the unattenuated signal and the signal as viewed through the canopy. And they had what's it called? Boston Dynamics. Anyway, they had one of their robot dogs tromping through the forest with a GNSS receiver. There's his paths in the middle plot. So I thought that was cool. Okay. Oh, and then finally, actually going in and digging up soil and measuring the soil moisture and other soil properties. Okay. All right, my last slide. This is his slide. This is Andrea's slide. Where do we go from here? Well, figure out how to incorporate how to parameterize and incorporate the permittivity of the forest floor into soil moisture retrievals, and then use the field data that's been collected to validate the VOD retrievals. Develop algorithms that apply globally. You see, I mean, this will start out with these experimental plots, but then you need to figure out how you're going to use ancillary data to develop, a lookup or dynamic ancillary data to use in the algorithms. They want to install more validation sites in forests, like obviously they need one in tropical areas. And then, of course, since everything nowadays needs to show value and impact. All right. Sorry if I talked over, and I can take questions.